With us today, we have Dr. Rajesh Bhayana, and he's an abdominal radiologist at the University Medical Imaging Toronto group and the technology lead for JDMI here at UHN. He's an assistant professor of radiology at the University of Toronto, and he completed his residency at the University of Toronto, where he was chief resident and pursued a clinical fellowship in abdominal imaging at Massachusetts General Hospital. Dr. Bhayana's research focuses on the practical application of artificial intelligence, particularly large language models, in radiology to directly improve patient care. His work addresses the current gaps in clinical care by optimizing LLMs to solve real-world problems, which has included projects to automatically categorize pancreatic cancer resectability from reports, identify actionable incidental findings, auto-generate histories for oncologic imaging, auto-protocol imaging studies, and automatically calculate cancer risk scores from lesion descriptions. Rajesh, we're thrilled to have you here with us. We're really looking forward to your chat. And with that, I'll hand it over to you.
Thank you, Kelly. Thanks for the kind introduction. And thanks, Shaf, Bo, Kelly, everyone at the UHN AI Hub for having me here today. As mentioned, I'll be talking about leveraging large language models or LLMs for clinical impact today. And as a clinical radiologist, that's the focus of my research in particular. Rather than looking at future theoretical applications of AI, I focused on how to use LLMs to solve real-world clinical problems now, and how we can implement them here in practice at UHN. So with that in mind, I want to start with 3 main points that are all related. So number 1, the intelligent optimization of existing foundation models already, in my opinion, enables many clinical applications that can improve patient care now. And that's because there are many clinical problems and inefficiencies that we see day to day that intersect with what is possible with AI today. And this is where we'll spend the bulk of our time here today, looking at what we are doing in radiology across the clinical spectrum, from when an order is placed to after the report is issued. Number 2, a lot of AI research in the world today happens in silos. So you have the smartest technical minds working on the technical problems like building domain-specific foundation models, but without the clinical expertise to understand the real-life clinical issues that they may solve. And so many of these technical papers contain obvious clinical errors, and the inverse is true too, where clinical papers contain obvious technical errors. So the main point here is that we must, in my opinion, more aggressively collaborate to make more impact, and that the UHN AI Hub is very well positioned to serve that role here. And then number 3 is that in medicine, we focus a lot on AI safety, bias, privacy, and other risks. And of course, these things are important, and they have to be considered. But we should not use them as excuses to sit on our hands. So for applications that are validated and offer concrete, obvious clinical advantages, we need to get these into practice in supervised settings sooner rather than later, in my opinion. If we know something augments what we do, improves care or efficiency, we should facilitate expedited deployment in safe settings. Again, the main focus of my talk is going to be point 1, but the other 2 are, of course, closely related. So I'll start with a brief intro to LLMs. Limitations, i.e. why we can't just throw these models into the deep end and expect them to work out of box in practice. Instead, we need to optimize these models for specific tasks. So we'll talk about how you can do that to unlock various applications. And then in the second half, we'll explore some of those applications, focusing on what we've been doing in radiology, and then wrap it up. So first, a bit of background so that we're all on the same page and we can frame how we think of LLMs the same way. So I think most people have interacted with LLMs through chatbots. And so chatbots is just a word that refers to an end user application that mimics conversation. So chatbots are not new. The first dates back to the 1960s. It was called Eliza, and it gave you largely pre-programmed responses to your queries. The original Siri and Google Assistant came a long way, released in the 2010s. They were chatbots as well, but still very limited. So no, we're not here to talk about all of these. We're here to talk about the most recent wave of chatbots like ChatGPT, and more specifically, the LLMs that underlie them. And again, these chatbots like ChatGPT are applications that are built using large language models. So for ChatGPT, you can select today one of many models like GPT-4o or reasoning models like o1 or o3 Mini. For the Google Gemini chatbot, you can also select one of the Gemini models like Gemini 2.0 Flash Thinking, for instance. There are many other companies making very high-end proprietary models like XAI, which just released Grok 3, and Anthropic with their Claude family of models that are very good at coding. So in addition to these state-of-the-art proprietary models, there are many open source models. Most famously, Meta's Llama series, like Meta's Llama 3, for instance. Also, DeepSeek made a splash recently, no pun intended. Similarly, you have the DeepSeek application, which is a chatbot application owned by a Chinese company. And then the LLMs that they're built on, which are open weight models that you can download and host anywhere if you have enough compute. Even here at UHN through Azure, for instance, we could host DeepSeek models, for instance, and do so safely. So namely, that's DeepSeek V3, the model that's analogous to the GPT-4o from OpenAI. And then their reasoning model R1, which is analogous to the OpenAI's O1 reasoning models. So that's a lot of letters and numbers in these names, which can be very confusing at first if you're not acclimated. But for now, most important is to distinguish these commercial chatbot applications like ChatGPT, in which inputs and outputs are owned by the respective companies like OpenAI. So these should never be used clinically or with any sensitive information. And in contrast, the LLMs themselves at the bottom, like GPT-4o, which are basically just giant neural networks that you can use securely or in a secure way in your own applications that are for healthcare if you access them correctly. So how do these LLMs work? And that's largely beyond the scope here, but I highly recommend this deep dive by Andre Karpathy, who's a thought leader on LLMs, used to work for OpenAI. This video is on YouTube. But essentially, these LLMs are large neural networks that are trained on massive amounts of text. And these neural networks are pre-trained to predict the next word or token in a sequence. So given a certain input or context, it tries to predict what's next in that sequence. And that's based on patterns that it's learned from that pre-training data. And there's knowledge that's inherent in that, right? So for instance, if the context was the most common cause of pancreatitis is, it might predict gallstones as the next most likely word, and then maybe alcohol as the second most likely word to come next. So for pre-training, it's helpful to conceptually, or how to think of it, I should say, as essentially compressing the knowledge of all of the internet data it was trained on into the model's parameters, kind of like a zip file. But it's a lossy compression. So we can think of the knowledge of an LLM that you interact with like a gestalt of the entire internet or a vague memory of the entire internet. And this image here is from one of Karpathy's talks. So pre-training produces something through this process called a base model, which is just a next word predictor. And then post-training involves fine-tuning that model or that giant model so that the next word predictors are actually a little bit more useful to us. For instance, like acting as a helpful assistant and actually answering our questions, which is often called the instruct model, which is kind of like what ChatGPT is. But why have these models become so good so recently? So very briefly, the three biggest factors to set the stage that enable this acceleration are one, the transformer model, or the architecture of the neural net. So that was introduced in 2017 in a paper called Attention is All You Need. Transformers essentially enable better understanding of context in sequential data and process data in parallel, which enables very efficient unsupervised learning. The T in ChatGPT stands for transformer. The availability of massive amounts of unlabeled internet data for pre-training. Again, the P in GPT stands for pre-trained. And then availability of massive amounts of compute, specifically massive clusters of GPUs, needed for both training and also inference, i.e. what helped make NVIDIA the single biggest company in the world. So LLMs increased in size referring to the number of parameters. I'm sure many of you are familiar with or have heard of scaling laws. The idea being that as you scale up model size, training data, and compute, model performance typically continues to increase, shown here as a decrease in loss as you scale all of these three things up in tandem. This is from the 2020 Scaling Laws paper from OpenAI. So it's an ongoing debate as to whether these performance gains are going to continue as we scale, acknowledging that we only have a finite amount of data available to us on the internet. But as models got bigger, they became more flexible. And so that's the takeaway from this first section. In this chart, if we have a chart here with model performance on the y-axis here, and number of examples given to a model on the x-axis. So smaller, more traditional models like the one in green need a lot of examples of a particular task to improve performance on that particular narrow task. Whereas much bigger models, like the one in blue, this one happens to be GPT-3, perform very well with only a few or even zero examples. So, i.e., they can easily be adapted to multiple different tasks without needing a lot of training examples. And so this flexibility to perform well on language tasks out of box was widely showcased in late 2022 when ChatGPT was released. So that's kind of what made the moment happen. So we found uses for it immediately, like writing emails, articles, computer code even. So early on, someone famously coded the entire game of Flappy Bird just by following ChatGPT's instructions. And the newest models now are very, very proficient coders. These models have demonstrated human level performance on professional and academic benchmarks, like comfortably passing the bar exam. Ultimately, language is the code of thought. It's how we think, including in healthcare. So this is, of course, very powerful. In medicine on USMLE questions, the models have significantly improved over a short period of time, with recent models performing very well on general medical questions. In radiology, we published some of the first benchmarks in any medical specialty demonstrating solid performance with GPT 3.5 and then a leap forward in reasoning with GPT 4. And this was exciting for the potential of these models. As a brief sidebar, it is important to note that multiple choice performance does not equal safe or effective care. So it does not speak directly to clinical utility. So to be clear, it would be an error to judge LLM performance like we judge humans, i.e. ChatGPT passing a board exam does not mean that it has the capabilities of that type of physician for many, many reasons. These models have limitations. But still, the early exploratory research has shown a lot of promise. So for instance, in this JAMA internal medicine paper, ChatGPT answered medical questions from patient questions posted to an online forum, and they found that ChatGPT's answers were more empathetic and overall preferred to responses from verified forum physicians. A key limitation here, of course, is that the comparison group was forum physician responses rather than standard of care. Still, very intriguing. As mentioned, these models are far from perfect, so I think that we need to balance the hype with reality. Speaking of hype, many of you have likely seen this meme, or maybe it's just all of the radiologists. Although I think the traffic in this picture on the right looks a lot like my daily commute on the Gardener, so I guess the joke's on me, no matter how you slice this one. But the reality is that these models have a tendency to hallucinate, i.e., as you know, produce incorrect or irrelevant responses. So when ChatGPT was first released, for instance, if you tried to ask for references, it often just made up fake references that don't exist. You all likely heard of that infamous case of a lawyer who used ChatGPT and ended up setting a bunch of fake cases in a lawsuit and then was disbarred. So remember, we have to think of LLMs as next word predictors that have a hazy memory of the internet's knowledge. Though hallucinations have been mitigated quite a bit in more recent state-of-the-art models and using certain tools that we may talk about later, they tend to hallucinate most in domain-specific areas like what we want to use it for in medicine. So as a result, there have been many articles that conclude that LLMs are not ready for clinical use. For instance, this Nature paper evaluated LLMs in clinical decision making and highlighted some of those limitations. So, namely hallucinations and misinformation, which we introduced. LLMs also lack metacognition. So, simply put, they don't understand their own limits and produce overconfident and incorrect responses. Knowing your limitations is one of the first things that we teach medical trainees. LLMs tend to struggle with complex reasoning. They can't do that much thinking per token prediction, and so make simple mistakes sometimes. They can perpetuate bias. They are sensitive to the quality of inputs, i.e., obvious errors in the medical record could be propagated. Amongst other limitations that I've listed here, I'm going to cover them in a little bit more detail in my review listed here that's designed to be a primer for radiologists and other clinicians. So given all these limitations, you might think it sounds like LLMs are not really medically useful at all. And it is true that these limitations do preclude us from just throwing LLMs out of box into the deep end and relying on them in medical contexts as medical generalists. But this is where we make a key distinction. So LLMs out of box are by nature general purpose. So they've been tuned for general use to be helpful, to be flexible, and to be creative. And that's what we were talking about in that post-training step. They were specifically created to be general, helpful, flexible, and creative. So we shouldn't really expect that they're going to work well for clinical decision making. And important point, that does not mean that they cannot be leveraged to be incredibly useful in medicine today. LLMs can and must be intelligently optimized for use in more narrow medical contexts. And this helps further mitigate or eliminate some of these commonly cited limitations and enable us to improve quality and efficiency in narrow domains. So what does this look like? So the main point here is that the inherent flexibility of LLMs means that they can be efficiently adapted and optimized to perform well on many narrow medical tasks. By narrowing the scope and optimizing the models, we can reduce hallucinations, misinformation, and bias. We can adjust parameters to make these models less stochastic. We can use them securely via local deployment or secure cloud that is PHIPAA compliant, like UHN's Azure environment, for instance. And in narrow scopes, we can limit the impact of suboptimal data if we're controlling the inputs. One of the main points that I want to get across today before we go into the clinical applications is how we can optimize these models to unlock powerful use cases in your respective fields. And that the flexibility of LLMs makes this process incredibly user-friendly. So we can't cover each of these in detail, but the classically described ways to optimize LLMs as an end user are one, prompt engineering, i.e. how we instruct the LLM in natural language and what information we give the LLM to perform a task. So this includes giving it knowledge in context or in its context window and providing it with a limited number of examples. Two, retrieval augmented generation or RAG, which is the single best way to introduce substantial knowledge or domain-specific custom knowledge to an LLM. Essentially, you're connecting an LLM like GPT-4o to your custom data. Basically, RAG will pull relevant custom knowledge into context when needed. So remember, if we think of LLMs as having this vague memory of compressed internet data, it's going to be hazy on the domain-specific or subspecialty knowledge. So by putting knowledge or high quality knowledge in the context window, it's like refreshing its memory, and it's going to be much more accurate when dealing in that realm. And three, fine tuning, which involves giving the model many examples of input-output pairs to actually adjust the weights of the model. Ultimately, you're better aligning the model outputs with your intended use case. So fine tuning is the best way to modify the behavior of the LLM to align with whatever task you're trying to give it. You can also very easily adjust parameters like temperature, which control how random or creative the model outputs are, for instance. So if you're to reduce the temperature, it's going to improve repeatability, which is often desirable in medical contexts. If this is all new as well, this can feel like a mouthful. But in reality, once acclimated, many of these things are very user-friendly to actually put into play. In particular, prompt engineering specifically is a very easy way to explore the feasibility of a new use case that you have very quickly. And that's prior to doing any other optimization if you need to. And prompting is often combined with these other forms of optimization to create useful applications. So, how does all of this unlock clinical applications? How do LLMs actually do that, and what do they look like? So, I'm going to use the radiology workflow from the time that imaging is ordered to after a report is issued to discuss how LLMs can improve care and highlight what we've done in radiology in both research and clinical contexts. So to orient you to this chart, on the outside of this image in blue, we have each step in the radiology workflow, including the requesting of imaging, the protocoling of imaging, the reporting of the imaging, and then once the report is issued, interpretation of that report by clinicians and patients. And then in red here in the middle, we have potential automations of these manual tasks, i.e. auto clinical history, auto protocoling, reporting tools, and then custom transformation of reports for both clinicians and patients. So there's actually a lot of commercial products that already exist in many of these spaces that are already promising improvements to efficiency and quality for clinicians and radiologists and support workers as well. But research and validation tends to lag far, far behind as expected. So some of the things that we've been working on here along this path include auto clinical history to improve the information we get, auto protocoling, various reporting tools like improving how we assign cancer risk scores and how we determine tumor resectability, and the things that we can do with that final report, including creating custom patient-friendly reports that meaningfully improve patient knowledge and experience in the clinic. So we'll only have time to briefly touch on each to provide a little bit of flavor and get you thinking about your own areas. But happy to talk about any of these in more detail in the question period or after. So let's dive right in, starting with the clinical history. So clinical history is critical in imaging, but this is often what we get. Follow-up. So what's the primary tumor? That impacts how we image and how we look at the images. Is the patient sick? Is there a specific question that we should be answering? Or even this one. This is a real one that I've got before. Rule out a diagnosis. Remember, the same imaging findings can mean different things in different clinical settings, so it actually matters quite a bit. Now, the fact that clinical histories often lack key details is not a new phenomenon. So this paper here at the bottom is from JAMA in 1963. It was titled "The Clinical History as a Factor in Interpretation." So this really is an age-old issue in radiology. There have been a lot of efforts over the years to improve on histories, but the literature suggests that histories may improve for a short period of time when you implement these QI initiatives, and then it tends to wear off as people go back to baseline. People get tired, people get fatigued, people have other things to do. So in oncologic imaging, we not infrequently live with suboptimal histories, sometimes not even mentioning the primary tumor. But using LLMs tapped into the clinical notes, we can auto-generate a structured clinical history, like we show here at the bottom, where at a glance I can see the primary tumor, ovarian in this case, reason for imaging, relevant tumor markers, presence of any acute symptoms or the clinical status, any previous surgeries or therapies, and this is curated based on what the radiologist specifically needs to know. And so we leveraged GPT-4 at the time, the LLM, to perform this task on 200 patients undergoing oncologic imaging, using relatively little prompt engineering and only a few examples given to the model. And so how did they do? So GPT-4 performed very well at extracting this information from the notes with an F1 score of 0.983 in this proof of concept for these extractions. And in short, LLM generated histories in the charts here in green were much more complete than current standard of care in blue. For instance, in the red boxes, we see that LLMs much more frequently included critical pieces of information, including the primary tumor, other secondary cancers, presence of acute symptoms, and history of surgery in that part of the body. And radiologists much preferred the LLM generated histories for reporting, highlighted here in green versus current standard of care in blue. So this study was recently published in the journal Radiology. This is also something that we're working on, hopefully bringing to our radiologists at JDMI. We can talk about, again, some of the risks, but looking at these results demonstrating very strong improvements over current standard of care, to me, it feels more wrong not to implement this as soon as we can. Next, once a requisition is placed, a radiologist needs to protocol that study, i.e., determine how the study is going to be done. As a bit of background, for instance, for CT of the abdomen and pelvis, we have about 40 different protocols or ways of doing a CT abdomen and pelvis here at UHN. And the protocol selection impacts care. So how we decide to image the patient determines what we can see, and for certain types of tumor, whether we're even going to see the tumor on the imaging. So protocoling is also a very repetitive and extremely time-consuming task. It's about 5% of a radiologist's day by most estimates, but we're going through hundreds of these requests. And protocoling can be applied heterogeneously because it can be complex and it's very repetitive, and people make mistakes or may not follow our internal guidelines or even know the internal guidelines. Having others protocol like technologists or even automating that process has already been a hot topic for several years in the literature. But the traditional methods and traditional models have previously demonstrated some inflexibility. So they're trained on historic examples to replicate what humans previously protocoled. They can't easily and quickly be adjusted for policy changes or new protocols because they're trained on historic data. And there's limited nuance in understanding of the text in the prompt itself or in the clinical history itself. In contrast, the flexibility of LLMs makes them a really good fit for this problem. So we can provide an LLM with detailed instructions that we can edit at any time if there's policy changes, and it might even follow those instructions more faithfully than a big heterogeneous group of residents, fellows, or staff in this narrow domain. So we can't go into the methodology into too much detail in the interest of time, but a brief overview of what we did, just enough to understand the results. So we took nearly 1,500 of the CT abdomen and pelvis requests. We had expert radiologist reviewers help define the reference standard protocol in direct consultation with our institutional guidelines. We developed a complex, very long prompt that provides detailed instructions to the LLM regarding when to use each protocol. So this was based on institutional guidelines, and we did iterative prompt engineering on 300 or using 300 example cases. We then split the remaining cases into groups, so into training set, validation set, and a test set. And then we created two different LLM-based applications for protocoling. The first, we used GPT-4o with the complex prompt that I described earlier only. And the second involved GPT-4o with the complex prompt, but also fine-tuned on reference standard protocols from the training and validation set. And then on the 548 test set cases, we ran each of the models and we collected the initial human-assigned protocol that was assigned in real-life practice. We then had reviewers categorize each of the outputs, and very importantly, the reviewers were blinded to whether the protocol was coming from a human or from an LLM. And the reviewers categorized them as follows. So it was either an exact match with reference standard, or if it did not match, it was one of either an equal alternative protocol, a reasonable but inferior protocol, i.e., against our institutional guidelines, but likely only slightly reduced diagnostic capability, or three, frankly inappropriate, where the protocol directly limits the ability to answer the clinical question. And we define the reasonable but inferior plus inappropriate to be suboptimal protocols. And of course, that allowed us to directly compare each of these LLM strategies and compare with current standard of care. So preliminary results, in this chart, you have human assigned protocols at the top. You have LLM with the prompt only in the middle, and then LLM with prompt plus fine tuning at the bottom. In dark green, we have exact match with reference standard. In light green, we have equal alternatives. In orange, we have reasonable but inferior. And in red, we have inappropriate. So firstly, right away, you'll see that LLMs match reference standard more frequently than human protocollers. They assigned suboptimal protocols, which are combining orange and red, less frequently than humans. You'll notice the orange and red bars together are smaller than the human assigned protocols. But you'll notice that the red bar is small for all, and there was actually no significant difference in the frequency of actual inappropriate protocols assigned by the LLMs versus the humans. And then lastly, in this particular study, you'll notice that fine tuning with labeled examples did not actually yield any further improvement in performance. So the middle and bottom bars are very similar. So for protocoling, which can sometimes be very complex, a complex prompt or prompting is all we needed to unlock this application at not only clinically acceptable levels, but in a way that stands to improve the alignment of the assigned protocols with our institutional guidelines. And so I'm happy to say that this is something that we are implementing for CT abdomen and pelvis this year at JDMI in a supervised setting where radiologists will still verify all protocols, and it should improve both our efficiency and the homogeneity of protocoling. Moving on to the report. So prompt engineering can enable complex clinical tasks like automated tumor categorization. And so for pancreatic cancer, surgery is the most important part of treatment, and local staging with CT largely determines management. So specifically, there are a finite number of imaging findings or key findings on CT that help determine if a pancreatic tumor is resectable, borderline resectable, unresectable, or metastatic. But the problem is that radiology reports are often complex, verbose, and radiologists don't often actually dictate the final resectability category using these criteria or NCCN criteria. So it can be hard for someone who's reading a report to know if a tumor is resectable or not, which is the most important thing to know. So we work closely with some of our HPV surgeons on this study, including Drs. Gallinger, Moulton, and Schwartz on this. And what did we do? So we used LLMs first to automatically generate synoptic reports here on the right from original reports. So we extracted key details for surgeons like involvement of major vessels like superior mesenteric artery, celiac artery. These are the key findings that dictate management. So they could easily pull that out and see that. And then second, we use the information in these synoptic reports to actually apply these complex NCCN criteria and categorize the tumor as resectable, borderline resectable, or unresectable. So for this first step of just extracting the information, we know that LLMs perform very well, and they did perform very well in this study. But the second step here is a bit more complex. So even surgeons and radiologists have variable knowledge of these criteria and apply rules heterogeneously. So we evaluated 3 different prompting techniques on this complex task. So first, we just relied on the default knowledge of the model, which we established as lossy. We just said, hey, go ahead and categorize this tumor based on this report as to its NCCN criteria. Second, we provided knowledge in context. So in the prompt, we laid out all of the complex NCCN rules in detail, acting as a refresh of that knowledge for the model. So the LLM can now refer to that knowledge accurately and then apply them to new cases. And then third, we used a prompting technique called chain of thought. And that can help with complex tasks. So in this case, we teach the model to think in smaller bite-sized pieces step by step. For this study, asking the model to first categorize each vessel. So the celiac artery is resectable, the common hepatic artery is borderline resectable, etc. And then take the highest category as the overall tumor category. And so how did they do? So on the y-axis here, we have the accuracy for categorizing these tumors. And we'll focus on the green here, which are GPT-4 results. So out of box, if you just rely on default knowledge of the model, it performed pretty poorly, 67%. But adding in context knowledge significantly improved performance to 83% accuracy, and then the chain of thought prompting even further to 92% accuracy on this very complex clinical task, over the 85% threshold that we had initially set with the surgeons. So this really illustrates the power of prompting, even for complex clinical tasks. You can't cram too much thinking into a single prediction. You need to kind of spread that out and have it think step by step. And this is exciting because we can apply similar principles to other advanced applications or complex applications in medicine. We also asked HPB surgeons to review a series of original reports from radiologists and the synoptic AI generated reports and categorize resectability as they were triaging referrals. And in short, at the top here, they were much more efficient using the AI generated synoptic reports, and we're actually much more accurate at interpreting the AI generated reports over the original reports. Switching gears, for women, ovarian lesions are very common, and trying to figure out whether they're cancer or not is obviously critical to dictating management. And for that, radiologists have something called ORADS MRI, which is a 5-point scale of the risk of cancer in a particular lesion. And that system helps improve communication with surgeons, but even more importantly, helps avoid unnecessary or overextensive surgeries in women who don't actually need that overextensive surgery with benign lesions. But again, the problem is that radiologists don't use this system enough. There are too many rules in the system, and in general, there are too many of these systems that radiologists need to keep straight and know. So what if AI could automatically help apply these complex rules to free-form lesion descriptions that could potentially automatically markedly increase system adoption and potentially accuracy in applying those systems, which would ideally improve care? Unfortunately, as mentioned, LLMs out of box tend to struggle with complex clinical tasks. So in this radiology paper, not ours, LLMs out of box did very poorly at assigning BI-RADS categories on mammogram reports. But again, this was done without any optimization, just thrown to ChatGPT. So the result is not surprising. For ORADS MRI, we tested 2 optimization strategies. So first, LLM only, where we provided GPT-4 with a detailed account of all of the complex system rules in context so it could follow them. And then second, we tried a hybrid approach where we first relied on LLMs to classify ORADS MRI features only, and then we passed those feature classifications into a deterministic formula to calculate the ORADS MRI score. The rationale here is that we rely on LLMs where they excel, i.e. interpreting complex language, and then use deterministic elements to apply these complex rules more reliably, which is sometimes where LLMs fail or get crossed. So on our internal test set, we found that the hybrid approach was 97% accurate compared to reference standard, which was significantly more accurate than the LLM only strategy at 89% and the originally reported scores at 88%. And so again, use of a tool like this could automatically significantly increase adoption and potentially improve accuracy in assigning those scores. There are many of these systems in radiology. We intentionally started with ORADS MRI and LIRADS, which are both systems that have good evidence for them. They're sufficiently complex to apply manually, and they're significantly underutilized today. And I'm happy to say that this project was one of the winners of the CDI, or Cancer Digital Intelligence Grand Challenge for responsible AI implementation. So we're working with the CDI team at Princess Margaret Hospital to responsibly implement this tool into practice, hopefully. So lastly, patients often read their radiology reports themselves, and sometimes before seeing a doctor. And since the reports are filled with radiologic jargon, this can be confusing and sometimes anxiety provoking for patients. I think a lot of clinicians see that when they see their patients. So there are actually a lot of startups in this space, like Scanslated is one that tries to help patients understand their reports by defining keywords, for instance, like this. Pocket Health has actually done some interesting stuff, including helping define certain keywords. But these are still relatively rudimentary in that they don't fully transform the report, as far as I know, to this day. LLMs, on the other hand, are really good at writing, so they're a perfect fit for creating patient-friendly summaries written at the appropriate grade level, English or other language, while still maintaining the meaning. So there's actually been a lot of research done to explore this use case for LLMs. So we don't have too much time to go into this one in too much detail, but and we actually haven't done that much in this particular space. But LLMs really haven't yet been widely adopted for this because reports are, of course, very heterogeneous. And the concern is that with a heterogeneous array of findings set in many different ways, the concern is that for some report types or for some findings or for certain language, LLMs may misinterpret language or hallucinate findings or give incorrect interpretations to patients, which could be dangerous. So we've actually been trying to work on this in a more narrow context alongside Dr. Nathan Perlis in neurology, who's been working on patient-friendly reports or has been working on patient-friendly reports already for some time. So very briefly, Dr. Perlis and his team previously created a patient-friendly report template that explains prostate MRI reports in a very simplified way. And so they work with teams to painstakingly define the right language to use, the right layout, patient-friendly diagrams so patients could understand where this was in their body, etc. And then they manually created these for patients and found in a pilot of 40 patients that these patient-friendly reports improved patient understanding. They were found to be more useful by patients. They gave them better knowledge and helped them know what to expect in clinic. So ultimately, it reduced their anxiety and allowed the in-person clinic visit to be more productive, informed, and fruitful. So that's great. Case closed. We should use this. But the problem is that it's not scalable. So it took the administrative team a long time to create each of these reports or patient-friendly reports from a report. You have to interpret the jargon in a radiology report with lots of tables, draw lesions in the right locations, put them into the right categories, etc., all manually. And then that would have to be checked by a urologist or the practicing radiologist, and that was an inefficient process. So it really was not feasible to have all patients who get prostate MRI to benefit from this. So we optimized an LLM to extract and classify the necessary information from this report and created a tool to automatically create the patient-friendly report. So now you can paste a report into the tool, and within seconds, it's going to generate a PDF that is a patient-friendly report shown here on the right. And it's going to, based on location, actually draw the lesion on the schematic in the correct location on that schematic diagram. And so we're currently validating the accuracy of this tool. It's still early days, but so far it's performed well. And we can apply it to other systems that are confusing for patients, like TIRADS for thyroid nodules. So ultimately, this was primarily enabled by LLMs performing multiple complex extractions, both quickly and accurately, which was previously not possible. So for those interested in LLM research, regardless of your area of expertise, when it comes to finding a good clinical use case for LLMs in your particular area, I think really critically thinking about the current clinical problems or gaps you see on a day-to-day basis that we experience in real life on a day-to-day basis. And then if you understand what LLMs are good at, trying to find the problems that live at that intersection. And when you use LLMs out of box without any optimization, I think the overlap here is actually where you can get useful performance is actually kind of narrow at present. But with appropriate optimization and even minimal optimization, that overlap grows significantly, in my mind, including a substantial proportion of the repetitive tasks that require language or thinking. So hopefully that gets you thinking about where you might want to explore applying LLMs in your own practice. So we don't have much time, but I just want to briefly touch on what's coming. We talked a lot about text applications because that's where my research happens to focus. But multimodal models refer to those where the inputs and or outputs can be more than one mode of data, like text, images, audio, etc. So this is not new, but it's progressing rapidly. And it's, of course, a very good fit for medicine where the patient data that we have is inherently multimodal. So text history in labs, medical images, pathology, etc. Multimodality also opens up new methods of interacting with LLMs. So it's not just a chatbot that you're typing to, but as many of you have likely experienced, you can have very natural, low latency conversations with LLMs, which is very applicable, if optimized, to interacting with patients in various regards. But you can also now do things like share your screen and interact with LLMs about what you're seeing on your screen. So it's perfect tech support for grandma or for whoever. I posted a video of Gemini interacting with and interpreting a CT live as I scrolled through it. And that video happened to go viral. I didn't watermark it. And then the video was unfortunately stolen and reposted by many people. And someone actually turned it into a video meme with Matthew McConaughey that went even more viral. That was making fun of radiologists. That was pretty funny. Um, and then next, LLM agents. Agents and agentic are the buzzwords of 2025 in this space. You've probably heard them being said over and over again. I think people use the word agent variably, but I think we should think of agents as autonomous systems that themselves decide how to achieve a substantial goal, where you don't need human interaction at each step. And then lastly, reasoning models, which I find particularly interesting. So recall earlier, we talked about chain of thought when categorizing pancreatic tumor resectability. So we established that since LLMs can't do too much thinking in a single token or word prediction, we kind of want to spread out the thinking into bite-sized pieces. And it reasons much better and does much better with complex reasoning when you spread it out like that. So we actually did this by chance a year and a half ago with this project in a very narrow problem that I showed. But reasoning models are now models that apply this kind of chain of thought automatically for every single problem. And so these are the O1 models, the O3 models from OpenAI. The DeepSeek R1 reasoning model, for instance, is also a reasoning model. These are really the new frontier and what's being pushed forward right now. So rather than just predicting the next word or token in the answer directly, using reinforcement learning, they're actually tuned to output a bunch of reasoning or thinking tokens first and actually think through the problem in a roundabout way. And then only once they've had a chance to think for a good amount of time, produce the answer. And it turns out that they generally do much better with complex reasoning in this way. So this is a real example that I just threw it this morning into O3 Mini. So I asked the model to determine the NCCN resectability criteria. And rather than jump to the answer, it paused and thought for 27 seconds and then output a bunch of intermediate steps, many of which are hidden by OpenAI, unfortunately. And then it came to an answer that in this case, it was a simple problem, was correct. DeepSeek R1 makes all of the thinking tokens public, which is cool. So here's an example of it of the raw thinking tokens, which is again pretty cool. So it says here, I'm going to try to figure this out. This is what the user wants. I remember that the NCCN guidelines categorizing tumors into resectable, borderline resectable, unresectable, and then it thinks through the process or the problem in a step-by-step way. So this is fascinating to me. It's obviously very applicable to medicine, where thinking and complex reasoning is so core to what we do on a day-to-day basis. So this is still in its early days. So sometimes it derails itself, makes errors, etc. But it gives you an idea as to where this is going and what the potential is in this space. So I'm running out of time. And in the interest of getting to questions, I'll skip over this section. But I think a lot of the AI research currently is happening in silos. And we ideally want to facilitate a more aggressive collaboration between clinical and technical people to do the most that we can. So in conclusion, most importantly, I think optimization of existing foundation models already enables many clinical applications that can improve patient care. We showed some examples from what we're doing in radiology today. We need a more aggressive collaboration in general in the world, but also we can facilitate that here at UHN through this hub between the clinical and technical people to make more significant impact. And then again, while safety is extremely, extremely important, we shouldn't use that as an excuse to sit on our hands. Where there are clear benefits, we need to take the opportunity to implement these tools in safe, supervised settings. So thanks for having me. Appreciate it. And hopefully I left a reasonable amount of time for some questions.
Thanks, Rajesh. That was an excellent and very, very clear presentation. So I think we all learned a lot. I think I'm going to open for questions. First, we have Barry and then Peter. Barry.
Thanks, Rajesh. I really, really enjoyed that. I appreciate the scope of work that you're doing. My specific question has to do with evaluation of outcomes of patients when you apply these technologies. So take the specific example, the grading of resectability or not when pancreatic cancer and CT scans. Looks like it works well. How are you going to determine if there's actually an impact on patient outcomes?
Well, I had a question as well while you answer that is if the report says it's not resectable because the SMA is involved, but surgeons at TGH would do a jump graph of the SMA and could do a complete resection. How do you you've just written that it's unresectable?
Yep. Yeah, so those are both very, very good points. I'd say to the first point, I mean, at present, we're looking at it in very narrow context, to your point. So we're saying, can it even do this complex reasoning? That's step number one. And we've been focusing on kind of, I guess, for lack of a better term, verifiable outcomes in the short term as these new technologies start to emerge. But I think that it's a great point because we can throw so many of these things at a wall and say, oh, look, we're improving everything. But if at the end of the day, you're not actually improving patient outcomes, what have you done? So I would say that the step one is finding these candidate applications that we know work in narrow contexts. And then the only way we know, should we throw a lot of money behind this idea or that idea is, okay, we have to have trials that are prospective and actually look at real patient outcomes and not just, okay, can it do this thinking? But I think it's kind of a natural progression as that's what's coming next. I'd say in the literature in general, I found that early days, it was just a bunch of tricks and people would say, here's an exam, answer this question. So that was, I think, the first stage. I think we're kind of, the literature is maturing now to, okay, let's use it for real life problems, but in retrospective ways and some prospective ways. And then the next step, I think, is kind of moving in that direction of let's really apply these things in practice. And then to Shaf's point, I think that it's important that it's very clear that, when you're applying these systems, those systems are named. So for instance, by NCCN, this is what it is. But of course, if you're using different criteria at your institution, it's going to have to be institutional specific. So that's going to be kind of related to local preferences, whether you even want that to be written in the report or not. And if not, kind of what maybe you just want kind of a transformation that makes it easier for you to consume what's actually involved, and that's all you want. And even that would be a potential win for efficiency and readability.
Peter?
Yeah, thank you very much, Shaf, Rajesh. Phenomenal work and a great talk. And, with reference to your, if you don't mind me, describing it as a horseshoe of progression, have you looked at LLMs or any of your colleagues sort of revisiting the guidance for the clinician around appropriateness, modality? In many cases, I'll be very simplistic as an endoscopist or gastroenterologist. We know there's a lesion, but we may not know whether ultrasound, MRI, CT is the best way to go. The patient may have had prior imaging. Based on that, we may not know what the best sequence or the interval may be. Have you been able to apply any of this? Because it looks like terrific work, and I suspect we could do that. Maybe you're staying out of that because of the various political and other, sort of challenges, but welcome your thoughts around that part of it.
Yeah, definitely. I mean, in the horseshoe, I don't know if you probably saw the first thing was clinical decision support. So I didn't mention it in the interest of time because I tried to focus on a few high yield things that we've been doing. So we in our particular group haven't investigated the clinical decision support in any depth. That being said, it is a ripe application for LLMs, and there has been a lot published in that area. So there was one where, this is an American study, so they used the ACR appropriateness criteria, and they gave an LLM a bunch of clinical scenarios, and they actually, using RAG, I talked about retrieval augmented generation, where it can pull the relevant chunks of data. It was connected to all of the long form ACR guideline documents, and it was actually able to apply and pick the best or most appropriate studies more frequently than some of the residents that they had put on this same task, for instance, who were tasked with interpreting those guidelines. So that was like a very early exploratory study that I saw initially, but it's definitely something. I mean, there are a lot of these decision support tools that are non-AI, that are kind of decision trees. The way I see it moving forward is it's kind of going to be similar to these decision trees that we have, but we can augment those decision trees by pulling certain details from the chart using LLMs. LLMs are really good at taking unstructured data and making it structured or classifying things. So if we can take simple classifications and we can say, okay, we know this patient's diabetic. We know this patient has X, Y, and Z. So we can actually move down the decision tree for you and make it more efficient for you to use that decision tree and then get the right imaging that you need. So I've seen some startups in that space starting to try to apply LLMs, and I think that really narrowing how you apply them like that is probably going to be the most safe way to implement them than just to be asking kind of a chatbot.
And the other thing, Rajesh, is that creating, I was going to ask a similar question about decision support. Creating decision support requires getting guidelines and so on, and it's a lot of work to get one decision support tree. So do you think that that's the way that large language models might help us to develop, clinician support?
Yeah, I mean, I actually know one of the radiologists in our group, I believe, had a company in this space where they kind of have all of those decision trees, and they're not using really AI at present. But I think that as a first step, kind of that's like the train track, and the LLM can kind of move down the track. I don't think it's kind of ready to say like, hey, let's just ask the AI and it'll kind of, there's too many different ways it can derail. So I foresee that as being the next or the first step into that, into leveraging LLMs for that type of thing.
Yeah, we're using that in the development of decision support for pleural effusions because it's evidence-based and it helps the physician decide what's the best test with the highest yield to order. So best for the patient and also saves resources.
Mm-hmm.
But it's only for one thing, pleural effusions, and then, going forward. So, but I think the nice thing about it is we don't have the risk of hallucinations or other problems. It's
Exactly.
Canadian guidelines for working up a pleural effusion.
Yep. They're
But
actually using it in the UK quite a bit and some of the hospitals there where they have, I mean, many of these things built out. And again, there may be risk of kind of hallucinating or making assumptions when you're pulling from the chart. But I think that's again kind of the best way I see that moving forward.
Great answer, Rajesh. It sounds like between Shaf and I, we can muster our colleagues to work both above and below the diaphragm with you. This is a great opportunity. Thank you.
I'm below the diaphragm personally, but I can I see the lung bases sometimes.
AI goes everywhere.
Yeah, exactly.
I think we'll have to wrap up here. I know there's other questions and stuff. People will contact you, but thank you again, Rajesh. That was a really, really great lecture. We learned a lot. It was very clearly delivered. Thanks.
Thank you so much for having me. Really appreciate it.
Bye, everybody.